Welcome back to Math 104. What is the range of scores which differ from the mean by at most 2 standard deviations, at most 2 copies of sigma? These are scores falling between a lower bound of 74.57 minus 2 copies of 8.01 and 74.57 plus 2 copies of 8.01. Here we're starting at the mean 74.57 and moving downwards by 2 measuring sticks. That's 74.57 minus 16.02, which is 58.55. So a score of 58.55 is exactly 2 measuring sticks below the mean. And the upper end of this range is 74.57 plus 16.02. So plus 2 measuring sticks. That equals 90.59. So this is the range of scores that differ from the mean by at most 2 standard deviations. Any scores between 58.55 and 90.59. Now let's be careful here. Between 58.55 and 90.59 means excluding 58, but including 59. So a score of 58 is a little bit more than 2 standard deviations below the mean. It's a little bit beyond that 2 measuring stick threshold, and a score of 91 would be a little bit too high to fall in this range. That's not really an issue when we look at this data set. There are no 90s or 91s here, but if there were a 91, it would be outside the range of scores that we're talking about. All of these scores, and this is the overwhelming number of them, fall within this 2 standard deviation range on either side of the mean. What percentage of data points fit this description? What percentage of data points differ from the mean by at most 2 standard deviations? All but 6 of them. That means 94 out of 100, which is 94% of them. This 94% number is not going to be the answer every time we look at a data set of 100 scores, or any number of scores. But we're about to see that for a very common type of data set, something close to this 94% is what we will typically see when we look at a 2 standard deviation range. This brings us to the empirical rule. Many data sets which arise in real life have an approximately normal distribution, or they are said to be normally distributed, which means that when you plot the data, you get something approximately bell-shaped in the very specific sense that approximately 68.26% of the data points lie within 1 standard deviation of the mean, as represented here, anywhere between the mean minus 1 copy of sigma up to the mean plus 1 copy of sigma. Approximately 95.44% of the data points lie within 2 standard deviations of the mean, so everywhere from the mean minus 2 copies of sigma up to the mean plus 2 copies of sigma. So all of this entire range here, this is a total of 95.44% of the data, and 99.74%, that's virtually all of the data points, lie within 3 measuring sticks of the mean, from mu minus 3 copies of sigma all the way up to mu plus 3 copies of sigma. Please let me emphasize, it is not the case that every dataset in real life looks like this. There are very important datasets that don't look like this. But for the many datasets fitting this description, these percentages are very helpful to know. So to be clear, this 34.13%. That means that of the 68.26% of the data points lying within 1 standard deviation of the mean, if the dataset is truly normally distributed, half of that 68.26% lives below the mean, and the other half of the 68.26% lives above the mean. The data within 1 standard deviation of the mean are split equally between below and above the mean. In general, when we talk about normally distributed data, we are talking about a data set that is symmetric in this sense. Similarly, with 13.59% of the data more than 1 standard deviation below the mean, but not quite 2 standard deviations below the mean, if you've got 13.59% of the data living in this range right here, then you've got another 13.59% of the data living in this range here, somewhere between 1 standard deviation above the mean and 2 standard deviations above the mean. Let's look at some real-life examples. Plotted here is the full set of 2010 SAT data. It's common for exam data to be normally distributed, or nearly so. You'll notice that in this example, it's not exactly true that it's normally distributed. If you look at this portion of the data up here and the corresponding portion of the data down there, we do not see the exact symmetry between left and right that would characterize truly normally distributed data, but in the grand scheme of things, this is somewhat close. Another classic example is height, although you will get something closer to a truly normal distribution if you have separate data sets for female height and for male height. Here we have plotted the heights of young adult males. This shows that the dataset is not exactly normally distributed, but it's close. For the sake of computation, let us suppose that we are working with a dataset which really is normally distributed. In particular, let us suppose that in the US, adult female height is normally distributed with a mean of 63.7 inches and a standard deviation of 2.7 inches. So this is just under 5'4". What is the probability that a randomly selected adult woman in the US has a height between 63.7 inches and 66.4 inches? In order to use this information about how the data really are distributed, we need to be able to describe these heights in terms of the mean and the standard deviation. Now 63.7 inches, that is exactly mu. That is exactly the population mean. 66.4 inches is something greater than the mean, and we would like to know how much greater. How many standard deviations above the mean is it? Well, isn't that convenient? It's exactly one standard deviation above the mean. 66.4 equals exactly 63.7 plus 2.7. In other words, mu plus one copy of sigma, one measuring stick higher than the mean. That enables us to read off the answer. We see that the probability we're looking for is 0.3413. There is a 34.13% chance that a randomly selected adult woman in the US, in other words, someone selected from the entire population of adult women in the US, has a height that falls within this range right here between mu and mu plus sigma. So the answer here is 0.3413. Let's follow up by asking, what is the percentage of adult women in the US whose height is between 61 inches and 71.8 inches? To answer this, we need to remember that mu equals 63.7 inches, and sigma, the standard deviation, equals 2.7 inches. In order to use this information, we must understand these numbers in terms of mu and sigma. Stare at this for a moment and think, how much is 61 inches in relation to mu and sigma? 61 inches equals the mean minus something. It's the mean minus exactly one measuring stick. It's the mean minus exactly one copy of sigma. 63.7 minus 2.7 brings us exactly to 61. How about 71.8 inches? 71.8 inches equals mu plus something. How can we figure out that something without necessarily just staring at it? Let's apply the same thinking we used earlier when we asked how many standard deviations above the mean is Pat's exam score. We can ask how many standard deviations above the mean is 71.8 inches. Well, 71.8 inches minus 63.7 inches will tell us the difference in heights. If we divide that by 2.7, that will tell us how many times 2.7 goes into this difference. In inches, this difference is 8.1 inches, and we want to know how many times does our measuring stick of 2.7 inches go into 8.1, and that is exactly 3 times. So 71.8 inches equals mu plus 3 copies of sigma. Now we really understand our range of heights. Our range of heights runs from mu minus 1 copy of sigma all the way up to mu plus 3 copies of sigma. We are talking about all of these heights in here. The answer to our question will be 34.13% plus this 34.13% plus this 13.59% plus this 2.28%. When we add these up, we obtain 84.13%. 84.13% of adult women in the US have a height within this range, or equivalently, a randomly selected adult woman in the US has a 0.8413 probability of having a height within this range. Before going on to the next video, answer the following questions. What is the probability that a randomly selected adult woman in the US has a height greater than 66.4 inches? And then a question that requires you to remember something about conditional probabilities. Suppose you know that a certain adult woman in the US is at least 61 inches tall, but you know nothing else about her. What is the probability that she is between 61 inches and 63.7 inches tall?